should I start? Can I start? Or
okay, let me make that announcement then, just for the sake. Hello, everybody. Today we have a special session where our three awesome GSIs will give an overview of their research, including open questions that can be project ideas for you in CS267. And so we're gonna start with Giulia Guidi, and each one of these presentations will be, I believe, 25 minutes or so.
Yep.
Okay, yours, Giulia.
Okay. Hi, everyone. It's a pleasure to, being able to talk about my research today with you, and I hope you will find it interesting. So today I'm going to talk about a few parallel algorithms that we develop in the context of the Novo genome assembly, and I'm briefly going to explain what this is. And this work is known to us and people that have read our paper as DBELA 2D. That basically stands for Distributed Berkeley Efficient Long Grid aligner initially, and then assembler in the future when we'll complete the whole pipeline. So let's start with what's a genome assembly. So we know that the genome, knowing the complete sequence of the genome enables us to study the organism in depth and characterize, and this enable further analysis like gene editing or like studying epigenetic variation. And this has many applications in agriculture or medicine, as we will see a little bit later. And here's an example of a genome. So, and something that is surprising, at least was surprising to me at the beginning, is that the wet genome or plants genome in general are usually way bigger than the human genomes, and something that it was crazy to me at the beginning. So for example, with this wheat genome has 17 gigabases. So bases is like nucleotides. So it's basically the characters the DNA string is composed of. And the problem when sequencing genome is that the sequencing technology based on chemistry and biology limitation cannot sequence the whole DNA in a single run. So what happens is that it sequences DNA multiple times and generate very short DNA fragments that we call reads. And based on the technology, we have like average lengths between 100 base pairs are like up to like 10K, but even more actually with more modern technologies, but these are like average number. And in order to account for the fact that we sequence only small fragments, and so it's harder, to reconstruct the sequence, we sequence that redundantly. So basically, we have this parameter that is called depth. That means that each location in the genome is sequenced at least depth time. So for example, it could be like 6 in this example. Usually like, again, based on the technology, it can be usually between 15 and 100, 300 depth. That really depends. Also on the cost of the technology. And basically the process of de novo assembly a genome is that we want to reconstruct a genome that is unknown. So we don't have, like in this case, a reference genome, just based on these reads. So the idea is that we will try to overlap them. And you can imagine the genome, like de novo assembly, as like building a puzzle. And that puzzle is pretty hard. First of all, because you have no reference. So basically it's like you have these very small pieces and you have no idea what you are trying to build. So you don't know if it's a house or, I don't know, a horse or something else. So it's very hard. And the second is that, so again, it's very like, the pieces are very small. So it's like, not 5 to 6 years old, like complexity, but much harder. And the second thing to keep into account is that genomes have repetitions and repetitive regions. So it's like in this puzzle, you have, I don't know, 50% of your pieces that are blue or some kind of shadows of blue, meaning like it's just a sky. And it's very hard to, make sure where this blue piece goes with respect to the other ones. And the last part is that reads often includes errors. So this was much worse like a few years back. Now technologies are getting better. But the thing is that even like, a 0.5% can still create problems. So often like an error correction step is what you want. And the idea is that you might have two pieces that they seem to be almost like a match, of the puzzle, but they might not be. They might just be, similar due to some error or some mutation. Okay. So, but why, our team is interested in this is that like genomes are huge, especially after the sequencing, given that, you sequence the data redundantly. And especially in the case of plant genomes and metagenomes, where metagenomes is basically a mashup of multiple organisms. It's like you sample and like a piece of soil or like some ocean, like ground, and you sequence the whole environment. So you will have a mashup of different organisms in your data. And this can easily generate terabytes of data that is infeasible to process even, on beefy nodes with big RAMs. So the idea of a distributed memory de novo assembly is that this will enable to characterize very complex genomes like the plants one, but also reducing the runtime of smaller genomes. And this, can impact a lot of sciences like energy, health and medicine, and environment. So our work mostly focus on long ring sequencing data. And that's, if you're curious about other kind of sequencing data, we can chat about this offline. But for today, we will focus on this kind of data that has the advantage to be very long. So, the average length of the reads are around 10, 15,000 base pairs. And the downside is that they contains more errors. Based on this technology, it can be around 0.5% up to 15 or 20%. And when using this kind of data, the standard, the most commonly used assembly paradigm is the overlap layout consensus. And this paradigm works like the first step, you want to find overlaps between reads, and then we will show how we do that. But in this step, you just identify pairwise overlaps. Then in the layout step, you try to arrange this overlap in such a way that you have like a meaningful structure. Like in this case, we can see that, they connect to form like a linear like solution, a linear like sequence. And in the consensus step, you want to merge this into the layout. So I see a question. When we mean for reads is sequence of DNA. So it's nothing computer science related. It's simply the way biologists do. How we can know if the final result is correct? That's tricky. So what we do usually when developing this kind of build is that we start from the data where we know the ground truths, or we have a good enough idea of what the ground truth is. So we have the reference genome. And we try to tune our algorithm to return as good a result as possible. And when we don't know the genomes, what you do is you look at some final statistics like the length of your assembly, misassemblies, how many contigs, because ideally this is what happened. In practice, in the layout step, you will have some branching sequence. So it's not like as easy as it can seem here. So the final consensus is often not a single string that is your whole DNA, but it's like a bunch of shorter string that we call contig. And then you try to, put those contig together to make sure to get like a good representation of the genome. But make sure that your results are correct is like years long work. Like the human genome is still being, there is a lot of research on the human genome, but still today, they thought they'd completed the human genome in like around 2000, but then it kept, being improved as the research goes on. So looking at a little bit more into detail in the pipeline, these are the steps of our algorithm that are also the main step of, genome assembly pipeline in general. And we have a first step, k-mer counting, and then we will go into details of the first 4 phases here. Of the detection, pairwise alignment, that it can be optional based on the approach the algorithm takes and on the kind of data, and transitive reduction. And these are also for stages where we will have a few projects for students that might be interested in. So for first things, what we want to do is find these k-mers that are substrings of fixed length k. And these k-mers are used to find matches between reads because we want to avoid, an n square operation between all the reads because that's very expensive. So we want to make sure to find some common seed and then run more expensive operations such as pairwise alignment only on pairs of sequences that we know have something in common. So the first things we do is that we want to extract these k-mers. So if we have a sequence in this case and we decided our k is 4, we will extract the first k-mer, TTCA, and then we'll keep with a sliding window on 1 and extract all the other k-mers, and we'll count them. So what we obtain is like an histogram of frequencies. Then, based on some work that we did, and like, there is the reference at the end of the presentation, we can select the optimal k-mer length and the k-mer frequency interval that we want to use based on the error rate and the coverage. That is just another word for depth of the dataset. So, for example, if we have a 15% error rate dataset, a typical length is k between 15 and 20 based on the depth of the dataset. Because the idea is that if your dataset has a very high error rate, you want to keep your k-mer relatively small, because if you choose a k that is too large, you risk that each k-mer has some error in it, and that makes it very tricky for the algorithm later to find matches. So in fact, we see that if we lower the error rate, the k-mer length increase. And again, if people want to learn more about the model we use, I'm happy to chat about this offline. And so the idea, as I mentioned, is that we want to use these k-mers as, seed to find matches. So now I'm going to go a little bit into the detail on how the k-mer counting works, mostly because one of our project ideas is about the k-mer counting. So I want students, to know more or less what's going on here. The k-mer counting is MPI only, and it's composed of 2 main steps. So in pass, more than steps. So in the first pass, we have the input sequences that will be, distributed across different processors. And each processor parses its own reads into k-mers, as we see in the previous slides. And once we have this, each processor locally will estimate the cardinality of these k-mers. And then there will be a parallel reduction, a global reduction. So each processor will obtain the sum, the global cardinality estimation. And then this will be broadcasted to all the other processors, and we create a local Buluc filter. A Buluc filter is a probabilistic data structure that allows us to count k-mers. Mostly, we need the Buluc filter mostly because we want to make sure that in our final counting, we don't include k-mers that appear only once in the dataset, that are like the vast majority. But we don't want this because they are completely useless, because if they appear in only one read, we cannot use them to find any overlap. And most of the time are simply errors. So in our first step, we basically compute the cardinality and initialize the Buluc filter. In the second step, we again have the sequences local on the processor parses them into k-mers, and then we hash the k-mers and find the owners. So each k-mer will be hashed to a value, and that value will correspond to one single processor. So, and then the k-mers will be redistributed using an all-to-all communication to the final owner, so that a given k-mer is always sent to the same processor. And once the k-mers are received, we again check if the k-mer is already seen. If not, we discarded that. Sorry, we counted that. And in final, we once we have check the Buluc filter, we count them locally. And this is because, again, each k-mer, like a given k-mer, like CCTA, that k-mer has always been counted by the same processor, always ended up in the same processor. And as I mentioned, this is MPI only. And the idea is to be able to integrate, to add OpenMP support for the k-mer counting in order to have hybrid parallelism. And this mostly because our other step of the pipeline, as we'll see, have also OpenMP parallelism. But having MPI on in the k-mer counting, it forces our whole pipeline to run with multiple MPI processes, like multiple MPI processes per node. While what we will have if we could have OpenMP supporting the camera counting is having multi-threading within a single node and one MPI process per node. Okay, I see that I have like only 10 minutes left, so I need to speed up a little bit. I can go into more details, for people that are interested in this project then. So once we have counted our k-mers, we will build a sparse matrix where the k-mers are the columns and reads that are our DNA sequences are the rows, and each non-zeros is the position of the k-mer J in the read I. And what we do is then we transpose the matrix to obtain a k-mer by sequence matrix and multiply the two using a semi-ring abstraction. And this means that using this custom semi-ring, we substitute the multiply operation of the standard sparse matrix multiplication with an assign operation and the add operation with the add and concatenate operation. So what we obtain in our candidate overlap matrix C is a read by read matrix, like sequence by sequence matrix, where the non-zero is the number of shared k-mers and the position of those k-mers on both reads. So yeah, just a note, in practice, we compute the whole matrix, but we only need to do the pairwise alignment that is the next step on the lower triangles to avoid to do the redundant computation. And as I mentioned, this is MPI and OpenMP together. So this is the algorithm that that we use to implement the distributed sparse matrix multiplication. But for the sake of time, I will skip over this, even because I'm sure you will see this during the next lectures. One thing to mention is that when we read the input sequences at the beginning, they are distributed like in kind of like 1D way, as we can see on the left of this drawing. But what we want is that those sequences to match the 2D decomposition that we have in our matrices. And so what happens that as soon as we have read the data at the beginning, we start communicating the sequences according to a 2D decomposition. And this is nice because what happens is that potentially the communication of the sequences overlaps with the k-mer counting and overlap detection, so the sparse matrix operations. So when we arrive like at the end of the sparse matrix multiplication, we mostly already have all the sequences on the processor, and the wait time to finish the communication is usually relatively small. So now what we do is that we want to compute a pairwise alignment on the matrix C in order to remove those pair of reads that might just have a match, by chance. Maybe, there was errors or like repetitive regions. And so we want to make sure to remove data that are not good enough. And this is what the third project is about. So basically, pairwise alignment is used to find similarity between two reads, and it uses like a dynamic programming algorithm that takes ODM and time, where M and N are the lengths of the two sequences involved in the alignment. And we use a special kind that is called seed and extend, meaning that we start from the seed, that is the k-mer that the two sequences have in common, and we extend alignment to the left and to the right until either we reach the end of one of the two sequences or both sequences, or the running score falls X below the best score that we see in that point. Because the idea is that if we start seeing a lot of errors or a lot of mismatches between the two reads, we don't want to keep doing the alignment, because we already know that we want just very good alignment. So we don't, waste computation to do that. And if this is, our initial match, a possible alignment is this one, where we extend the left and right, and the vertical line means a match, and when there's none, it's just an error. Or so we have a mismatch in the case of C and G, and an insertion in the case of G and none. And again, I'm happy to talk more about this with people that are interested in these projects. And the idea is that right now we have a CPU implementation and a GPU implementation. And when we run the GPU implementation, the CPU is idle. So we just offload all the alignments to the GPU. But what we would like to have is implement a work stealing from the GPU, from the on the CPU side. So if the GPU is full, we will also have the CPU doing something and not just staying idle in the meantime. So I see that, well, I already mentioned like briefly the project, so I think I can quickly go over the transitive reduction. So the idea of the transitive reduction is that now we have this post-alignment matrix. So we are already like pretty confident that the non-zeros, that the connection we have in the matrix are pretty good and they are not errors. But the thing is that we have a lot of redundant information. And in order to make the next step easier, we want to clean this kind of graph and remove redundancy. And we do this with this transitive reduction. But one thing we have to do is that we need to move from an overlap matrix, that is what we have right now, to a string matrix. So in a string graph or string matrix, the edge between the two reads is no more the overlap length like it is in the post-alignment matrix, but it's the suffix of, if we have an overlap between R1 and R2, our edge between R1 and R2 is AT in this case, and so on and so forth. And what we want to do in the transitive reduction is to retain as much useful information as possible. And this means we want to remove longer overhangs, because like longer edges or longer overhangs means that we have a shorter overlaps, and we don't like that. We want to keep the longest overlap. So in this case, what happened is that if this is the input matrix slash graph, this is what we obtain at the end. And this is also, okay, so we need to change a little bit the encoding. So, and this is pretty straightforward to do. It's very bug prone. I have to do that a lot of time before getting it right, but it's something that you can do while, like, as soon as you finish the alignment. And this is also performed using a lot of matrix operations, where the first operation that is also the most compute intensive is the squaring of the error matrix. And this is because we want to find the two hops neighbors between each pair of reads. So, and in this case, we also use the custom semi-ring abstraction, where the multiply is an add operation and the add is a min operation. And this is because we want to find the shortest path. And so this is what we obtain. So in this case, we will multiply and obtain our neighbor matrix N. And we will perform a few operations that I'm going to skip over in the sake of time. And this is mostly to account for possible errors. And what happens is that we check for the edges that are transitive, so that can be removed, and we obtain this matrix I. And then we element-wise like multiply R times the logical negation of I in order to remove those edges that we have identified as transitive from the main matrix, and we obtain the final matrix S. In practice, this operation is repeated multiple times until, in order to find the 3, 4 hops neighbors, until we don't have any more reduction. So the number of those non-zeros is unchanged between S and R here. And R square, so the squaring of the matrix, is the most compute intensive operation, even because many of the other operations, like this sample, like for example, this one is not, it's element-wise, so it doesn't require communication. Okay, so this is basically what we obtain in the end. And again, I know I rushed through this, so if you have questions or want to learn more, feel free to reach out to me after this. And this is a few results. So this is strong scaling of our algorithm, so the whole pipeline. And this is, I think, okay, so on both Summit and Corey Haswell. And the scaling, like it's pretty good overall. Like this is C. elegans and Homo sapiens that are two, like Homo sapiens is decent size, C. elegans is not too big. But yeah, we get a pretty nice scaling, so we were happy with these results. And here's a breakdown of the runtime on Corey Haswell for the Homo sapiens dataset. And we can see on the left that we have the full pipeline. And on the right, we have the same breakdown without the alignment. And we can see that the alignment takes most of the time. And that's one of the reasons we want to optimize. And this is CPU only. We weren't using GPU in these results. So this is why we want to use GPUs for the alignment and possibly hybrid CPU and GPU. Then if we look at the right part, we see that this sparse matrix multiplication in the K-mer counting, sorry, in the overlap detection is the one that takes most of the time after removing the alignment part. So that's also the reason why we would like to have a GPU implementation. Oh, that's what I forgot to mention. I will briefly go over this right now. And finally, we can see that the transview reduction takes very little time. So this is a summary of the project. And I think one I forgot to mention at runtime is the second one. We would like to implement the sparse matrix multiplication on GPU using a custom semi-ring. Out there are a few implementation of sparse matrix multiplication on GPUs, but they are not flexible enough to use a custom semi-ring that is crucial for our application. So we would like to have GPU-based SPGM using our custom semi-ring. Okay, so I think I'm only 1 minute over. It's pretty good. Yeah, just feel free to reach me out. I hope you learned something and you find it interesting. And I'm just, I think we are just gonna move to Alok's presentation right now. Okay, let me stop sharing this.
Cool. Okay, let me share my screen. Where'd Zoom go?
Thank you, Giulia. That was great.
Cool. Can you see my slides?
Yes, and the right set of right view.
Perfect. Let me open up the chat too, so I can have that open. Okay, cool. All right. So hi everybody. In case you haven't met me already, my name is Alok. I am a second-year PhD student here, and I work with Kathy and Aydin. And I'll be talking about, just like what Giulia did, I'll be talking about the work that I do primarily. And what I do is essentially what's known as communication avoiding graph neural network training. And I'll start pretty much at the basics. If you're not familiar with graphs, I'll talk a little bit about that first. And if you're not familiar with graphs, the truth is you've probably already experienced graphs in the real world already. Because graphs model a huge number of things that we have in our day-to-day lives. So for instance, if you've driven on a road networks are essentially graphs. And if you're on Facebook, for instance, social networks are also graphs. And the reason is graphs model essentially connections between entities. And so for instance, in a social network, these entities could be users, and a connection between two users could represent if they're friends or if they have some sort of relationship between them. And we typically call these entities, like users in a social network, we call them vertices or nodes, and these connections we typically call edges. And we have like an example graph on the left here, for instance, where we have 5 different entities and an edge between 2 vertices if there's some sort of a connection between them. And so this is what a graph looks like in a sort of abstract mathematical view. But if we wanted to store the graph, we can use essentially, we can use a matrix to store the graph, essentially. If we have 5 vertices, for instance, we can store this graph as a 5 by 5 matrix that mostly has zeros, but will have a 1 in an entry if it represents an edge between 2 vertices. So for instance, here, we have an edge from vertex 0 to vertex 1, and because of that, we have a 1 and that particular entry of the matrix. And we call this sort of a matrix a sparse matrix because most of the entries in this matrix is a 0. But we do have a few 1s that correspond to edges in our graph. So we have, I think, 7 or 8 edges here, and we have just as many 1s in our sparse adjacency matrix. So this is just sort of to form the foundation of what graphs are and how we can do some machine learning on graphs later on. Okay, so I see a couple questions in the chat. Is adjacency matrix the best way to represent graphs for efficiency on large computations? And adjacency matrix doesn't have to be sparse. Okay, yeah, so I guess to answer both questions, the first question is adjacency matrix the best way for large computations? So I think typically when we talk about adjacency matrices in, like, I guess the data structures algorithms course here is 61B. Typically we say, oh, these matrices take O of n squared space. And so when you have a large graph, this tends to take up a lot of space. In reality, most of these graphs tend to be sparse. And so you don't actually store like a dense column major matrix like you did in homework 1, for instance. You just store these what's called non-zero values. You just store these ones and you just assume that everything else is going to be a 0. So you don't actually take up n² space in practice when you store these so-called sparse adjacency matrices. And that makes them useful for larger graphs compared to storing an n by n dense matrix. The second question is, adjacency matrix doesn't have to be sparse just because we don't have a strongly or fully connected graph here. Yeah, you're right. It doesn't, typically graphs are sparse, which means that we can represent them with a sparse adjacency matrix. If this graph was fully connected, if there was an edge from a vertex to every other vertex in the graph, then yeah, we would have to use a dense adjacency matrix. But typically graphs are on the sparse side of the spectrum. And so we can use a sparse adjacency matrix to store them. So this again is just to form the foundation of what graphs are, so that we can apply some deep learning and graph neural networks to graphs essentially. And I'll briefly go over why we're even focusing on graphs at all, because I alluded to this a little bit earlier. But the truth is, graphs model a huge number of different problems that we find in both the real world, but also the sciences. So for instance, I've already talked about social networks and transportation networks, or road networks in particular, and how graphs can model those. But even in something like proteins, for instance, we have graphs that can model protein-protein interactions, where we could have a vertex that represents a protein and an edge between two proteins if they have some sort of a relationship between them. And even in materials discovery, we could have a graph that represents a molecule where an atom is a vertex, and an edge between two vertices represents if those two vertices have a bond between them, like a chemical bond. So graphs can be used in all over, like social networks, transportation networks, and also all over the sciences as well. They come up in a lot of different areas. And so because graphs are in some sense ubiquitous, we also have this ubiquity of machine learning problems that we can address on graphs. We have problems like graph classification and edge classification. And we also have node classification, which is the problem that we focus on here. And just to explain what node classification is for a moment, just as an example, let's say I give you a social network where we have a label on some of the vertices. And again, these vertices represent users. And we can have a label on users that says, is this user a celebrity or not? And so if we have a social network where some of the vertices, we know which ones are celebrities and which ones aren't celebrities, we can use that information to predict whether other nodes in our graph are celebrities or not. So we have some vertices where we know which ones are, we have labels on some of these vertices, celebrity or not celebrity, and we can use that to predict labels for the unlabeled nodes in our graph. And so that's just a toy example of node classification, but this comes up in a lot of other problems as well, from protein function prediction in a protein-protein interaction network, and also text classification, for instance, in a citation network. So the TLDR here is graphs are useful. They model a lot of different problems. And there's also, on top of just problems on graphs, there's also a number of machine learning problems that we can address on graphs. And here we mostly focus on the problem of classifying each node in a graph in one of a few different categories. And so if you already know a little bit about deep learning, and it's okay if you don't, this is just one slide, you might be wondering, why don't we just throw a CNN, a convolutional neural network, at a graph? We already use them on images, maybe this could work on a graph. But the truth is, again, CNNs are specialized for images. And you can think of an image as a sort of special case of a graph, where each pixel is a vertex. And each pixel, each vertex essentially has pretty much 8 neighbors. Most of the vertices in this graph have 8 neighbors. But graphs aren't as well structured as images. You could have a graph where a vertex has like 5 or 6 or even 100 neighbors. And so you need to generalize the convolution from scenarios where the graph is very structured. Most vertices have the same number of same number of incoming and outgoing edges, to a different scenario where the neighborhood around a vertex is a lot more arbitrary. So we can't exactly just throw CNN at a graph and expect it to work. We need to be able to generalize the CNN in a sense to work on graph data. And so to run machine learning or deep learning problems on the graph, we use what's known as a graph neural network. And I'll talk a little bit about how to construct a graph neural network, I guess, just how they actually work. But before I get to that, essentially what we take as input is two different things. We take the input graph as input naturally, but we also take into account feature vectors per vertex in the graph. And so if this were a social network, for instance, if this were a graph representing the Facebook, like the Facebook graph, each of these feature vectors could represent meaningful information about a user. So it could be age, favorite movies, I don't know, how many people mention this person on the internet, something meaningful about the user. And we take that along with the graph as input. And to construct a GNN from here, let's say we wanted to construct a two-layer GNN, we essentially have layers of the vertices in the original graph and an edge between two vertices if that corresponding edge exists in the original graph. So for instance here, if we look at vertex 1 in our GNN, we have an edge from 0 to 1, 1 to 1, and 2 to 1. And that's because in the original graph, vertex 1 has edges 0 to 1 and 2 to 1. And we also include this self loop as well for every vertex in the graph. And so this is how we construct the GNN. But why do we construct a GNN this way? The reason is the core operation of graph neural network training is what's known as this aggregation step, where we take every vertex in the graph and sum up the feature vectors across each vertex's incoming neighbors. So for instance here, if we wanted to run GNN training, we would take vertex 1, iterate over all of its incoming neighbors, 0, 1, and 2, and sum up the feature vectors. And we do this for every node in the graph. And because this so-called aggregation step is the core operation of graph neural network training, we construct the GNN this way just to make it easier and explicit, or just to make this operation easier to do in a sense. And so that was one step of the that was one of the aggregation steps. If we wanted to do this again, we can just hop over to the next layer of the GNN and do the same exact thing for vertex 1 here. Iterate over 0, 1, and 2, and sum up the feature vectors. And so that's the gist of how to train a graph neural network. I'll flesh out the details a little bit. And essentially we can talk about graph neural network training in terms of 3 steps. We first need to initialize the feature vectors per vertex in our graph in layer 0. We can also think of this as the input to the graph neural network. And then once we have these input feature vectors, we go over each vertex in the graph and do this aggregation step where we sum the neighbor's feature vectors for each vertex in our graph. And then once we do that, there's also this 3rd step where we apply weights to these vector sums. That is, we multiply these vector sums with weight matrices. And these weights are what the neural network actually learns over time. These are essentially the parameters for the network. So that's what a GNN looks like. This is essentially how a GNN training works. Oh, there's a question in the chat. This effectively turns the initial graph into a DAG. Is that right? Yeah, yeah. You can think of a GNN as a directly acyclic graph. Yeah, there's no back edge from a layer to a previous layer. So yeah, that's one way you can think about a GNN. Yep. So again, this is the gist of how to train a graph neural network. But what's the actual problem here, or is there a problem? The truth is there is a problem, and the problem is these graph neural network models tend to be very, very big. Specifically, they take n times f times L space, where n is the number of vertices in our graph, f is the length of the feature vector, and L is the number of layers in our graph neural network. And this comes from the fact that we need to store a feature vector per vertex in our graph, per layer in the graph neural network. And to just give some context here, the number of vertices, and that could be anywhere in the millions, maybe even a few billion for very large graphs. F, the length of the feature vector, is typically about maybe like a few hundred. And L, the number of layers in our GNN, is typically about 2 or 3. GNNs don't tend to be very deep. But altogether, this is too much space to fit on one GPU. And in case you don't know, most deep learning training is done on GPUs, and GPUs tend to have a lot less memory, maybe like 16 gigabytes, 32 tops. And so these models won't fit in their full form on a GPU. So I guess I have, how much time do I have? 15, I think. Okay.
Yeah, like 10, 15, yeah.
10, 15, okay, thanks. Okay, yeah, so that's the issue with graph neural networks. They tend to be very big, but this isn't a problem that we haven't seen before in deep learning. We've done distributed deep learning before. Why is this any different? And the truth is, when we do distributed deep learning in its current form, for instance, if we try to do distributed deep learning on image classification, for instance, what we typically do is we take the entire set of images that we want to train on, and we sample from that data set, and we can run these samples independently of each other. But when we do this sampling procedure, this mini batching procedure on images, when we take a sample of images, we don't need the rest of the images in our training set. We sample a batch of images, we can ignore the rest of the training set and just run training on this sample of images independently of everything else. But that's not true in graphs, because if we take a batch of vertices and we just want to run training on those vertices, we can't just store those vertices in the graph and train on these vertices independently. And the reason goes back to the core operation of graph neural network training, which is this aggregation step. Because remember, for each vertex, we need to sum the feature vectors across each vertex's incoming neighbors. Which means if we take a batch of vertices and we want to run training on this batch, we need to also store the neighbors for those vertices. And if we have two-layer GNN, we need to store the neighbors of the neighbors. And so we don't actually save space here when we do this mini batching procedure. And so in this work, we typically focus on full batch gradient descent just to sort of circumvent this issue. And so how do we actually do distributed deep learning training or distributed GNN training in our framework? What we essentially do is we take the whole model. We don't do any mini batching or anything. We take the whole model and we distribute this model across multiple devices. Specifically, what we do is we formulate GNN training as a series of sparse times dense matrix multiplication operations, and then we distribute these matrix multiplications across multiple devices. So I guess I need to speed up a little bit, but this is essentially what we do. We model all of graph neural network training as matrix multiplications, specifically sparse times dense matrix multiplications, and we distribute these matrix multiplications across multiple devices. And so I'll just talk a little bit about what GNN training specifically looks like in terms of matrix operations. And so if you're not familiar with neural networks, there are essentially two steps. There's forward propagation and backward propagation. Forward propagation is what I've discussed already, where we do this neighborhood aggregation step per layer in our GNN. And backward propagation is essentially going through the network in reverse and applying some matrix multiplications there to essentially correct the weight matrices and tune them. And so here we can see that these are essentially the matrix multiplications that you need to do for graph neural network training. To give a little bit of intuition here, if we look at the forward propagation equation, for instance, we're multiplying three matrices. We're multiplying this A transpose matrix, H, and W. And the reason we do this is A is our adjacency matrix for the graph. Remember that matrix that mostly has zeros but has a few ones in there. We take this matrix, and by multiplying with H, where H is the feature vector matrix, where we have the feature vector per vertex in our graph, by multiplying these two matrices, we do this aggregation step where we sum up the feature vectors across each vertex's incoming neighbors. That's all summarized by this A times H matrix multiplication. And then this W matrix is the weight matrix that we apply to all the vertex sums. And this is what's tuned in the neural network training. When this is what the neural network actually learns over time, how to tune these weights. And when we take a deeper look at these matrix multiplications, we see that we're not actually using a diverse set. We're using essentially two different matrix operations. We're using SPMMs, which are sparse times dense matrix multiplications. This is just a short way to represent that, SPMM. And then also DGEM, which is dense matrix multiplication, exactly what you implemented in homework 1. And so if we take a deeper look at these four matrix multiplication steps, in a sense, the only four that you need in graph neural network training, we see that we're only doing essentially two types of matrix multiplications, SPMMs and DGEMs. And between these two operations, you might be wondering which one actually takes more time. Do we spend more time on SPMM or do we spend more time on the DGEM operations? And when we take a look at a visualization of, like a matrix visualization of the forward propagation for graph neural network training, where we multiply the adjacency matrix for our graph, the feature vector matrix that we have, and these weight matrices, we can see that the bottleneck of graph neural network training isn't DGEM, it's this SPMM operation, where we have to multiply this huge, sparse but huge adjacency matrix for the graph with this huge dense matrix that represent all the feature vectors. This A times H operation takes way more time than multiplying with this small weight matrix W. And so if we want to speed up graph neural network training, if we want to distribute graph neural network training, we need to be able to distribute this sparse times dense matrix multiplication operation. We need to distribute this SPMM. And so how do we actually do that? How do we do a distributed sparse times dense matrix multiplication? Well, there'll be a lecture later on in the class that goes into this in a little more detail, but just to talk about this very briefly, you can represent matrix multiplication in general as a sort of computation cube. If we take a look at the cube on the left, for instance, each face of this cube represents a matrix. So we have matrix A, matrix B, and our output matrix C. And so this is our computation cube, and each sort of grid point within the cube represents a single multiplication operation that we're doing. And if we represent all of matrix multiplication in terms of this computation cube, we can distribute matrix multiplication by slice and dicing this computation cube in multiple different ways. And by slicing and dicing this computation cube, we get different classes of distributed matrix multiplication algorithms. And if this is going over your head right now, you'll see it again later on in class. I think Jim gives this lecture on distributed matrix multiplication. But for instance, if we divide this computation cube into these slabs, we get what's known as 1D algorithms. And what this means is essentially all the multiplications that happen on this slab of the computation cube. All of that is sort of owned by one processor. And you can divide the computation cube in multiple different ways. You can, if you divide it into these prisms, you get 2D algorithms, and if you divide it into these smaller cubes, you get 3D algorithms. So, okay, I guess I have
5 minutes.
5 minutes? Okay, that's fine. So I'll talk a little bit just, so again, there are multiple classes of these distributed matrix multiplication algorithms. And I'll hone in just as an example onto this 1D algorithm. And essentially, the way this 1D algorithm works is we take our matrices, our input matrices A and H, and we divide them into block rows. So for instance, here we have two processes, process 0, process 1, and each process owns half of each input matrix. And to do a distributed SPMM, what we effectively do is we take each block row of H, broadcast it to all the processes, and what each process does is it receives a block row of H, multiplies it with a portion of the block row of A that it has, and adds this to a running sum. And you do this once you do this for every block block row of H. Once you broadcast every block row of H, you get a resulting matrix that is essentially the result of A times H, but now it's distributed across all the processes that you have, P0 and P1. The reason I talk about this 1D SPMM just as an example is this leads into a couple different project ideas that have crossed our mind. One of them is to make this 1D SPMM algorithm into a sparsity-aware algorithm. What does that mean? Right now, what happens is when we take a block row of H, we take the entire block row and broadcast the entire block row of H to every other process there is in our process universe. This isn't always necessary though, because if we take, like, let's say for instance, process 1 has a column of A that has no non-zeros. This entire column is full of zeros. What that means is now we don't need a whole row of H. By broadcasting this row of H, all we're doing is saying, here's a row of H process 1, and process 1 isn't actually going to use that because there's nothing to multiply that row of H with in its subblock of A. So one potential room for optimization here is essentially don't broadcast every row of H, just broadcast the rows of H that are actually necessary for a process. And by doing this, we can drastically reduce the communication volume for our 1D SPMM algorithm. So that's one process, or one project idea. The second project idea is essentially to implement an asynchronous SPMM algorithm, where right now, essentially what happens is we go through these steps of broadcast a block row of H, do a local matrix multiply between the block row of A that you have and the block row of H that you just received, and then do this again, broadcast another block row of H and do another local SPMM. But you might be able to overlap the broadcasts and the local SPMM operations to reduce the amount of time needed to do this 1D SPMM algorithm. So essentially what that means is while process 0, for instance, is doing a local matrix multiply, it's also simultaneously receiving a block row of H that it'll need for the next local matrix multiply. And so by overlapping these broadcasts with local SPMM operations, we might be able to, in the ideal case, have the total running time, but in general, we might be able to get some substantial speed up here. So those are our two main project ideas. I'll just wrap up by saying we've done some communication analysis just to show that these algorithms, when you apply them to distributed GNN training, can provably scale with the number of processes. So for instance, here, our 1.5D algorithm scales with the number of processes. For one of the bandwidth terms, our 2D and 3D algorithms also scale with the number of processes. And this shows up in practice when we actually run these algorithms. So this yellow bar, for instance, these yellow and whatever color this is, gray, I guess. These colors represent the communication. And you can see when we increase the number of processes, the communication volume goes down. And what this means is the algorithms are actually scaling as we increase the number of processes. So overall, what am I trying to say here, I guess? What I'm trying to say is graphs are everywhere. Graphs model a lot of different problems. And because graphs model a lot of different problems, there's this sort of ubiquity of machine learning and deep learning problems that you can run on graphs. And so that's what's led us to implement this distributed graph neural network training framework. And within this graph neural network training framework that we have, there are a couple project ideas, namely making these distributed SPMMs sparsity aware and making these distributed SPMMs run asynchronously. So that's what I have.
Thank you, Alok.
I guess, yeah, for sure. I guess it's Melih's turn now, unless there are other questions.
I don't see any outstanding questions you haven't answered. So thank you again. That was great. And
all right, I guess I'll
yes,
start
Melih, it's yours.
Okay. So does everyone see my screen okay?
Yes, we do.
Yep.
Great. So I'll begin. I'll just quickly introduce myself. I'm Melih Elibol. I'm a fourth-year PhD student affiliated with the RISE Lab and Bear Labs, and I will briefly go over the Ray project and then follow that up with a presentation on Namas, a project that we recently started in the RISE Lab that is built on top of Ray. Okay. So let's begin. What is Ray? Ray provides a task parallel API and actor API built on dynamic task graphs. So here at the very bottom layer, we have the Ray execution model, which is dynamic task graphs. And what that essentially means is that as tasks are submitted to the Ray system, they're executed immediately. And dependencies between tasks are identified at runtime dynamically. Immediately above that layer, we have the Ray programming model, which is a task parallel programming model, along with actors. And I'll go into examples on both of these programming models in a bit. On top of that, we have libraries and applications, and this is basically what you or I would develop. And Namas is one of these libraries built on top of the API. So I'll briefly go over the Ray architecture. This is just a very simple example. In Ray, there are two node types. One is a head node, and the other is a worker node. The head node consists of a driver. The driver is essentially the Python program that executes the application written on top of Ray. And that lives on the head node. And the head node can also hold one or more, or even 0 worker processes. The worker nodes also have worker processes, of course. They don't have a driver, but all node types have this process called a raylet. And the raylet is comprised of a local scheduler and a local object store. And the local object store can be thought of as essentially a cache, in-RAM cache of object references and the actual objects that those references point to. Along with the object store, the head node will also maintain the global control store. And the global control store can just be thought of as a lookup table, a massive lookup table that tells you on which nodes objects are currently cached. All right. So the core Ray API, the API has expanded quite a bit since I began working on Ray. But the core API is essentially comprised of these 4 key functions. The put operation will take any Python object and put it into a local object store. And it'll immediately return an object reference. So put is an asynchronous operation. And the object reference can be thought of as a future. I mean, it's essentially a future. The get operation will block the driver process until the object reference that's being requested has been either computed or actually put into a store or transmitted over the network to wherever that get call is being invoked. And it will return a list of objects to which those object references point to. The remote function is actually a meta function and is applied to Python functions and returns a remote function that can be executed dynamically by Ray. And Ray, under the hood, sort of deals with the scheduling and can be thought of as a way of performing operator placement. So the operation will be placed on a node that makes it as quickly as possible to execute the function with whatever load, with whatever data is available on that node. And when the remote procedure is actually executed, some data might be transferred between nodes. And finally, the remote function is the actual invocation of a remote function. And that can take any number of arguments, including other object references, and can return a list of object references as well. So in this way, by sort of chaining together remote functions, you create a dynamic task graph. Okay, so we have one question. Does this comply with delayed execution model? Yeah, so it's basically a delayed execution model. It's not lazy evaluation, however. It does execute, again, it's a dynamically executing task graph. So while the concept of a future kind of corresponds with the idea of a delay, it's under the hood executing operations as they come through the Ray system. So it's slightly different. Yep. All right, so best to just go into an example here. So we have two functions, two Python functions. These are just ordinary Python functions. And one of them is just going to generate an array of zeros given the shape. And then the other one is just going to perform a dot operation between two inputs. The MP prefix here is the NumPy library. So we're sort of using the NumPy library in this example. So in order to create remote functions, we can just use the Ray remote decorator, and we immediately get remote functions. So now, once we have these remote functions, we can invoke a special function on those functions called remote. And that's the way we invoke remote functions. The remote functions can take actual values within the driver. So they can be literals, they can be objects, and they can also be other object references. So in this first line here, we have reference 1 and reference 2 that are returned by the calls to the 0 function. And then reference 3 is taking those two references and then executing the dot between the two references. So all of those three operations are asynchronous and return immediately. However, this bottom, the operation at the very bottom, the Ray get, will block the driver until reference 3 is resolved and will return the value for reference 3. So we can also create actors using Python classes. So here we have a simple example of a stateful class that maintains a counter. And we can create the actor by simply adding the Ray remote decorator as we did with the tasks. So it's very easy to sort of create tasks and actors, and really kind of allows programmers to focus on what they need to do instead of thinking too much about getting too much into the imperative operations involved in parallel computing. So with actors, we can instantiate the actor by calling remote on the counter class, and we can invoke the increment operation. Basically, any member of a class that's been made an actor becomes a remote procedure that can be invoked with the state of that actor. So these increment operations are incrementing the value that's being maintained by the actor. So these are stateful objects here. And then finally, when we invoke RayGet, the same thing as before happens. We can invoke RayGet on a number of different references, and that will block until all the references that have been invoked have been actually computed. So here's a simple diagram describing the parallelism that the operations in this example provide. We have the 0 operations that return references, and then the dot operation that depends on those references essentially will wait until those references have resolved before carrying out its computation and emitting its reference. So there's some parallelism that happens between the 0 operations and then the dot operation is obviously not parallelizable, except if, for example, within the task you did some kind of parallelism, which is definitely a possibility. And then we have the actor process. And the key thing to note here is that the actor process will guarantee the execution order of the operations that are invoked from the driver as they are invoked in the driver. So the first operation that's invoked is reference 4, and then reference 5. And essentially, these will just execute serially within the actor process. So that's sort of a distinction between tasks and actors. And the way you sort of achieve parallelism with actors is to just create many of them. So one cool thing you can do with actors is you can basically pass actor handles around. So what this basically means is that you've created an instance of an actor, and then you can pass it to, for instance, another task that can invoke remote procedures on that actor, and also invoke ray.get on those actors as well. Actors can also be passed to other actors, and so you can basically achieve some kind of communication among all actors when you're working with actor handles. However, there's a pretty high risk of achieving deadlock if you're not careful with how you pass around actors and how you invoke actor handles. Okay, so that's it on Ray, and now I'm going to just go into my presentation on NumS. Looks like I have about 10 minutes, so I'm going to, or 15 minutes it looks like, so I'm going to move through this relatively quickly, but the slides are online, and if anyone has any questions about this or any interests, then they can just contact me directly. So Ray does actually, under the hood, use shared memory per node. So the actual nodes, I'll just quickly go back. The nodes here, the object store is a shared memory system. So it's actually using shared memory to communicate within each node. And so in that way, you have sort of a shared memory as well as distributed memory parallelism. All right. So let's see. Let's talk about NumS really quickly. So what's the problem here? Why did we develop NumS? So both Ray and NumS are Python libraries, and the Python computing community, scientific computing community, isn't as sort of adept, I think, or familiar with a lot of the parallel computing concepts that we've covered in class today. I think in class this semester thus far. I think a lot of those concepts are pretty advanced, and they're quite uncommon programming models in Python. So NumS is aiming to make terabyte scale data modeling easier for that community. We have an abundance of very fast compute devices and libraries to manage parallelism among those devices, right? And as I mentioned, advanced parallel computing concepts and algorithms are somewhat of a challenge, I think, for Python users or scientific computing users of Python. They're kind of used to easier APIs. They're expecting something easy to use like NumPy or scikit-learn or something like that. So that's why we're working on NumS. And so the question is, what can we do to make numerical computing at these scales accessible to Python programmers, or more accessible, more widely accessible? So it makes sense to just sort of examine some of the trends, and this is what we did when we were thinking about NumS. We see that basically we can't expect faster CPU and GPU clock speeds. That's, I think, pretty clear. CPU memory is abundant, but shared memory has physical limitations. And here what I mean by that is basically you can achieve more shared memory, but you have wires that you have to deal with. And of course, there's wires even in distributed setting, but creating large shared memory devices, I believe, would be extremely expensive and not very accessible. So the key thing that we're sort of looking at here, and I think a shared sentiment among the people in this class, is that distributed memory approaches are a good way to achieve parallelism. We saw MPI and other systems that allow for distributed memory parallelism, and here we're going to sort of try to develop something that's a little bit easier to work with. And so there's some challenges that arise when you try to develop a high-level language in order to achieve some of the stuff that we can achieve more imperatively using a language such as MPI. So here we're sort of really relying on increased network speeds and GPU interconnects in order to sort of allow high-level language to be developed on top of low-level systems. All right, so what are the existing solutions? I'll try to go through these quickly, but basically we have NumPy that sort of scales vertically, and there's some limitations to its parallelism capabilities. We talked about MPI, and while MPI provides a solution for NumPy, TensorFlow, PyTorch, and these types of libraries to achieve parallelism, they require training on MPI or similar SPMD programming models in general. And yeah, so that's why we started NumS. And it's a numerical cloud computing system that automatically translates NumPy to optimize distributed memory code. So really the big challenge with this project is the optimization procedure. And I'll hopefully have a moment to talk about that. So I'm going to try to speed things up just a little bit, just so I have enough time to talk about projects. So what's the design? We have at the core of NumS the actual application. So this is the application that sits on top of Ray. We have block arrays that the NumS application makes use of in order to maintain block partitioned arrays across Ray clusters. And the block arrays are comprised of blocks, and the blocks implement unary, binary, and arbitrary operations by calling into a compute interface that we define within the NumS application. And the compute interface carries out those operations using the system interface. And finally, we have a store interface to actually load data that's external to the system to Ray into Ray in an efficient manner. And so in its current state, we have as the compute interface NumPy, we have as the system interface Ray, and as the store interfaces, we have S3 and distributed file systems. And the point here is that we've really sort of focused on decoupling the system, compute, and store interfaces from the core NumS application, so that in the future, as things change or if requirements change, we can try out different system interfaces. One example here is that we've implemented a GPU system interface recently that can perform basically the same set of NumS application operations extremely fast. So we have GPU support, and we're also looking into potentially providing support for other system backends. I think some of those projects are out of the scope of this class, so I'm not going to propose them as projects, but basically trying to do something like MPI or UPC++ as a system interface on top of NumS would be interesting. All right, so the execution on Ray is carried out as follows. So we have this very basic NumS application, and essentially what we have is a procedure that distributes read requests to workers. Those the workers actually perform the read requests on behalf of the driver by querying a storage system, and the storage system responds with the data. The worker then returns the actual data, and the RPC call the result of the RPC call will be put into a local object store. Okay, so that's essentially how RPC calls work in this particular API example. Finally, as long as there are references to those objects within the driver node and the driver process, the garbage collection system in Ray will not remove those objects. So as long as you have references to those objects, they're guaranteed to actually exist in the system somewhere. So that sort of gives you a sense of how data is loaded into the system. And now we'll sort of talk a little bit about how operations are carried out within the system. Really quickly, we have futures that comprise the arrays. And so here we have a basic matrix vector operation. The matrix vector operation is performed, and basically the operation is composed of promises. And we've done some sort of PL work to ensure the correctness of this composition. But basically, this final add function will return an object reference, and that will be something that you can later use something like ray.get to obtain the value. But we have high-level operations or high-level APIs to make this easier with NumS. So how does a system like NumS achieve parallelism? Well, there are two things that happen here. Anytime you access elements of an array, a new block array is generated. So here, all these array accesses that are highlighted generate new block arrays. And when those block arrays are operated on, the low-level blocks perform the actual operations, and those operations are submitted to Ray, and the Ray dynamic task graph will begin executing those operations, and any tasks that are independent will be executed concurrently. So that's essentially how we handle array access dependency resolution. And so in this way, we can achieve parallelism at any level of granularity. So one heuristic that I think we may have already seen in class, or that we will see in class, is the block cyclic heuristic. I won't go over this mainly because I think we're already going to cover it, but it's a way of balancing load on a cluster by basically viewing a cluster of nodes as a grid of processes in some sense. So I won't go over it, but this is used to load data in, but it is not used to actually carry out operations. And this slide shows why. It's not a good general solution for all operations. It's good for some operations, like element-wise operations. But I think in order to achieve good performance on all operations, you need to sort of think about which layout works best for various different operations. And that's sort of a more heuristic approach that you could take to developing a system like this. However, we took a different approach, and we developed an optimizer in order to achieve the parallelism, which I'm not going to have time to go over, unfortunately, but the slides are up. If you're interested in it, check it out. So I'm going to just kind of go over the slides very quickly. So we have an optimizer composed of 4 core components. This slide basically lays out the procedure for carrying out a element-wise addition using graph arrays that the optimizer leverages in order to optimize computations. This goes through sort of different representations of a tensor dot operation and what the optimizer will do in order to optimize the objective. And we show here empirically that we achieve quite good results, near optimal results based on the objective that I presented previously. And then we achieve really good benchmarks. We achieve something about 3 to 6x speed up over Dask and Spark on the logistic regression problem using the Newton method, and a 10 to 20x speed up on basic linear algebra operations over Dask. Dask is another system that's that does something similar to NumS, but it's built on a completely different distributed system. All right, so there's a open source project you can check out. And let's talk about project ideas. I at compile time, we can sort of look at optimizations of tensor dots, and this will sort of explore different ideas about how to block partition arrays and where to place the operation. So it's a sort of interesting compile time optimization project. We can work on providing sparse array support via sparse probabilistic matrix factorization. I think this would be a really fun project. We can implement various notions of matrix inversion, ideally with guarantees on numerical stability. We can also implement any linear algebra operation that's not currently supported by NumS. We can implement statistical machine learning models such as Gaussian processes, K nearest neighbors, naive Bayes. I think all of these would be really fun projects. And finally, empirically, we see that our optimizer achieves near optimal results. I didn't get a chance to go over it, but one final project is more theoretical in nature and asks a question: can we prove a bound on the NumS optimization algorithm using L2 norms, which is an easier space to sort of work with these types of theoretical questions. Okay, so it looks like we don't have any other questions, and I'm going to end the talk here. And I'll hand it over to Aydin, if you want to make any closing remarks or any other announcements.
There was an announcement I assume everybody read from Giulia. Before we close this session, I recommend everyone to go back and read that about projects. And if you want, Giulia, you can say it verbally before we close. But thank you, Melih.
Yeah, so the idea is that if there are multiple groups of students that are interested in the same project that we presented today, we will use our first come, first serve policy. And if you receive requests from individual students that are interested in the same project, we will suggest those students to work together on the project. And a couple of more things, there will be a lab tomorrow on MPI where we will talk about, discuss some parallelization strategy for homework 2 part 2 at 1, and the link, Zoom link is on Piazza. And we will release the proposal assignment this afternoon. But you have time until March 18 to submit it. So, okay, I guess we'll
thank you to all the GSIs for their excellent presentations, and thank you for joining us. See you next week.